So now we have a discussion being led by Rob and Julia. And I guess I'll just leave it with you and I'll help. If I see some questions on Slack that you didn't notice, I'll pipe in.
Great. Okay. Can you hear me?
Yes.
Great. Okay.
Yes.
So so the organisers asked myself and Julia to lead a discussion on jet interaction with the environment. So what we're going to do is I'll start off with a couple of slides discussing some relevant recent results from Meerkat, and then Julia had some points she wanted to make. So the idea is that Sarah and I, between us, will try and moderate the questions coming in via Slack, and Julia will manage the room. Julia, I presume you're now standing up there in person.
Yeah.
Okay. So some of you will be aware we've been running this program on the Meerkat radio telescope for the last 3 years, where we essentially monitor all bright X-ray binaries and a number of other sources, typically GRBs and type 1a supernovae. So this movie that you're seeing here is actually the radio emission over the first 2 years at typically weekly intervals as monitored by the Thundercat project. So it's quite reminiscent of the RXTE movie that we all used to show at these conferences 5 or 10 years ago. And what you see is that it's very nice. It's essentially a real-time monitoring of the jet activity and particle acceleration, which is going on in our galaxy below about equatorial declinations. And you can see a whole load of old favorites in here, which have been discussed at this meeting already and will be discussed in future. So a lot of interesting results have come out of this program, but I think the one that's got me most excited and is most relevant to this particular discussion is the aspect of seeing jets decelerating as they propagate into the interstellar medium. So those of you who know this field will know that prior to about 2019, we had in the previous, well, 50 years, but really about 20 years of looking for these things on and off, had observed 2 good examples of microquasar jets decelerating into the interstellar medium. So the poster child for this and the very famous example was XTJ1550, which when it outburst in 1998, Stefan Corbel and myself found in 2000 that there were radio lobes which hadn't been there previously, and that led to a couple of years of study. By that point, by the time we observed those jets, they were already brightened and strongly decelerated in the interstellar medium. There were also a few data points on another source, H1743. In the last 3 years, though, there's been something of a revolution in this area, and a couple of these results you'll hear more about, I think, tomorrow. I'll call it the Meerkat revolution. It's slightly disingenuous because at least at least the first 2 results I'm going to show here actually also had large contributions from other radio telescopes. But what we're now seeing is that with Meerkat, because of both the fact that it has a very high surface brightness sensitivity and the fact that we're doing this weekly monitoring of sources, is that we're actually finding these jets, and we're tracking them to much larger scales than we used to previously. So typically jets would disappear at a scale of order 1 arc second, and we had no idea at which point they terminated. And I would argue this really is the way to get the energy in the jet. So this is the result from MaxEJ 1535. So in the first 3 plots, you're going to see it's essentially time against angular separation. This is a paper by Tom Russell, who may well speak on this tomorrow morning. And there's an initial phase which looks quasi-ballistic, and then there's significant evidence of deceleration at late times. And again, in this case, you're tracking the sources now to 5 or 10 arc seconds, which is further than nearly all X-ray binary jets had been tracked previously. Then there's the beautiful example of MaxEJ 1820, where the deceleration was first reported in Bright et al., also in Espinasse et al., and most comprehensively in Wood et al. In that case, you see decelerating ejector. Francesco Caratenuto's paper, which I think he will talk about tomorrow, shows again this quasi-ballistic phase and brightened and decelerated ejector at separations of over 25 arc seconds in the interstellar medium. And we have another one, which I'll just call Jet 4 for now, which is in preparation, where we're seeing very strongly decelerated jets on a short physical scale and strong rebrightening. So what we're essentially seeing now is that after 20 years of seeing almost nothing, we're picking up about 1 case per year. And I don't have time to say much about this, but I think this is really the way to get the energy in the jet. If I could just make a quick broader comment, I've been been doing some work on GRBs recently, and like several other people on this conference, and this is how I would describe the comparison of the X-ray binary and GRB fields. The GRB fields have very advanced and refined theory on how jets propagate in the interstellar medium and how we see them. And of course, this theory is being applied to the neutron star mergers, and the quality of their data is essentially very poor. So they have, they have typically some power law rise and decay for a single event, and that's all they've got. The quality and quantity of data we have for the X-ray binaries is absolutely extraordinary, and the GRB field would die for it, but our models are very poor. So I would say the Van der Laan model, which has been the mainstay of modeling for X-ray binaries for a long time, is just wrong. And probably, at least in some aspects, the blast wave models, which are applied to GRBs, should be being applied to X-ray binaries now. Okay, so those were my quick points I wanted to make on jets and their interaction with the interstellar medium. And then Julia had listed some more general points here. So Julia, do you want to talk through these points?
Okay, yes. So thinking to this new detection that really change the numbers, the first question that one can ask is whether these jets are fully changing our view of this detection are fully changing our views of jets and large-scale jets. And so these are mainly related to major outbursts. So should we rely our view of jets in microquasars only on this detection, or what about the low power jets? Whether there is a way to estimate how frequent less powerful ejection are and how important. So not to have a biased view of jets phenomenon in microquasars. So this is the first point on which I would like to ask the audience. Then there is dynamics and the energetics. So this new detection involve VLBI also observation that led to the detection also of the jet speed. Of course, it's very important. It was key to get better estimates on energetics, but are our observable enough for the estimates that we need? And the assumptions are still valid. For example, we keep relying on equipartition, and maybe we have different view on this, but is equipartition still fine during, if we assume blast wave models, which implies equipartition, which implies also sort of equilibrium stage. Then we need to measure angular sizes, and can we rely on the radio observation that we have right now? And for example, I was involved also on some recent work where we were believing at the beginning to resolve a jet, and then when we had the multi-frequency radio observation, we realized that in fact there was some broadening due to the interstellar medium. So like some caveats on how do we interpret observations, and also what kind of other measurements we need to test GRB's model and other kind of models also for particle acceleration in jets and dynamics. And for example, most of our observation rely on radio and X-rays. And so what about the other bands? I've seen also some works on infrared. I think there was also some recent paper by Sarah Markov on possibility of having this ejecta detected in infrared, and so another hint on the discussion. And finally, on the interactions, I haven't seen much about the impact of these jets on the ISM. We assume that there is a cavity, and at some point the jets are impacting against the cavity walls and start decelerates. But apart from few detection in the last years, I haven't seen much. And as also concerning how they affect the nearby environment, there was like few, like one maybe in the last conference work on ALMA data suggesting that the jet action could induce star formation, star formation, but in the last years I haven't seen anything more, and I'd like to hear if there is something ongoing. And finally, also looking from the side of the jets, because I'm working mainly on Aegean jets. One of the last new recent things is that low power jets can be in fact more important on the galaxy impacting the galaxy environment because they have a more prolonged action on the ISM, better coupling, and they are more numerous. And so again, coming back to the first questions, is it okay to stop to this powerful ejecta, or should we consider also the faint jets? And I see also from yesterday's discussion that we have different flavors of jets that could be created in the state transition. I think was Samuel Barnier talk. And so what happened to these jets when they go into the space when they leave the small scales? So open to the questions, starting from the first, or okay, go ahead. So there is one question by Pop here.
Can you hear me? Yeah. Actually, yes, about these jet flavors, so blunt force Nayek or blunt force pain. Actually, from the candidates you show, are we sure that they are black hole candidates, and are there signature of this interaction between jets and interstellar medium for neutron star, and do we see any differences between the two type of object? I guess no, but
I can respond quickly for the ones that I showed on the previous slides. 3 of the 4 we are pretty confident as we can be without a dynamical mass measurement that they're black holes. The 4th is probably also a black hole. In terms of neutron stars affecting the environment, so there's a very bright neutron star radio jet source called Circinus X1, CIR-X1, and this lives within its natal supernova remnant, which is only a few thousand years old, but you can very much see the effects of the jets from the X-ray binary distorting the supernova remnant in a way which is analogous to the way that the jets, in fact, from SS43 famously distort the W50 supernova remnant. And of course, I'd also point out that, you know, in SS43, we don't actually know whether it's a black hole or a neutron star. So my feeling is that, yes, you know, the jets from neutron stars can on occasion be as powerful or nearly as powerful as the jets from black holes, and you know, given the right circumstances, can also distort their environments.
There's a question from Asaf on the Zoom.
Well, it's a very nice result that you showed. When you look at these, at the data of these jets, do they follow a Sadov solution of their velocity?
So what you end up with the issue, which is the following, which is that if they start off with a gamma that's significantly greater than 2, then during the phase when they're decelerating from a bulk gamma of, let's say, 5 or 10, we don't know, down to 2, they look quasi-ballistic. You cannot distinguish them from ballistic. And that's essentially because beta is 1 during this phase, right? And you can show that actually, regardless of the angle or initial gamma, or the way that it falls off with time, you can only really start to measure the deceleration when gamma gets to around 2. So you cannot tell prior to that whether or not they're decelerating in any particular way. I think we'll be able to fit models, but I think it's really it's gonna be difficult. We'll only be able to see as they sort of become trans-relativistic and non-relativistic.
So they're still relativistic at this stage that you're looking.
I mean, so at the point, if I can go back quickly, at the point where you're seeing the deceleration, that's when bulk gamma is getting to be around 2. Prior to that, they could, this whole phase here, for example, if you can see my cursor, this may be that actually there was no deceleration at all, or it may be it decelerated from gamma 10 to gamma 2, and you wouldn't be able to know. I mean, there are of course other considerations like energetics, but you wouldn't be able to measure it in the proper motions. And the fundamental reason is, of course, between gamma 10 and gamma 2, beta is still 1, and beta is what determines the apparent proper motion.
All right.
I think I see Greg has his hand up. Greg?
Uh,
Yeah, I do. So one of the potential ways we could trace jet ISM interactions is by looking for signatures in the millimeter. In particular, I'm thinking of some of the line signatures. And I'm wondering, and I mean, you know, Alex has been doing some of this work for past outbursts, but I'm wondering if people thought, you know, whether we should be targeting sources when they're in outburst specifically for these shock signatures or for the signatures of ISM shocks.
I don't know. I mean, the case that you're talking about with Alex is a shock that's a large angular separation from Juris 1915. So has formed, you know, a long time after, and it's probably the result of accumulated energy input. So I don't know. Maybe there's something to be done there. There may be others in the audience who have an opinion on this also. Maria, I don't know if Maria is there or is online, has done some work in this area.
Yes, I am, if it's me. I think if you want to go to short time scale interactions, you have to look for radiation more than the jet. I'm not sure that the jet would give you, you know, something that you can observe real time. So from this point of view, I think that looking at a sourcing outburst or not is irrelevant. If you're looking for mechanical feedback, I mean, if you're looking for radiative feedback, but still, I think the scales are still too low.
So my understanding is that one of the problem is also in relating large scale with the action of the jet is also that it's difficult to establish whether they are co-spatial, for example, the cavities with the ejecta several times on galactic scale, at least. We don't have this problem in the extragalactic jets because it's easier to establish distances, but sometimes for cavities, it's difficult to be sure that the cavity is actually associated with the microquasar. Is it correct that?
I think, you know, that's a reasonable concern, and it's, you know, the burden of proof is on us to try and prove this each time. I know in the case, for example, of the radio lobe that appears to have been inflated around Cygnus X1, there is a point of view that this is a chance alignment with a background supernova remnant. I think that's probably incorrect because it looks like it's attached to a nearby H2 region for which we do have distance estimates, but I think, yeah, the burden of proof is on us to make the association. Are there more questions in the room?
We have a question, yes, in the room.
Okay.
So I'm Francesco Cardenuto. I just wanted to answer Asaf's questions before regarding the set of phase. So for example, in the case of the source I've been studying, which is Maxi 1348 shown here, actually in the deceleration phase in the final part of its motion, the motion of this jet is consistent with a set of phase. And you can see here in the plot, in the third plot, one of the best model, actually here the plot is small so you can see it, but tomorrow I will give a talk on this, showcasing this. It's consistent with a set of phase, such as the jet is actually accumulating matter on its way, and at some point the matter swept causes the acceleration of this jet, and it reaches a set of phase. And I think this was also found, for example, not only in Maxi 1348, but also in XCJ 1752, a paper by Miller-Jones et al., that the jet motion is consistent with a set of phase at the end.
Yeah, that's right. That's right. I should have mentioned that. You're quite right, Francesco. In this, in the non-relativistic phase here. Yes. Were there other questions in the room? I see a couple more on Slack.
No, here in the room for the moment, no.
Okay, then Maria and Stefan. Maybe Stefan has disappeared.
Well, I just wanted to comment on what you said about the millimeter observation. I mean, one of the difficulty in the past, I mean, was that the resolution of the millimeter telescope was not good enough in order to pinpoint, I mean, the precise, I mean, interaction of the jet, and the difficulty to have a unique signature of interaction, because sometimes you can have excitation of the light for various other reasons. So the problem is to have a unique signature. Now that ALMA is available, but the difficulty is to get the time for this one. and it's probably the better time to do now and to do the effort to do this. The problem is you don't know the time scale, you don't know exactly. So the TO is probably the best way to go. And so we should indeed pursue this kind of effort. And there's some work done in the past, but not very fruitful for this. And so, yeah, so I think Maria and Alex has been doing things on that, and they probably want to comment again on that.
Thank you. Alex.
Oh, thanks. Hey, I just wanted to kind of add to what's been said a bit about the interactions. So in regards to the SIG-X1 bubble 2 and other sources, another thing that we have to worry about is when we can have like other contributions creating these kind of cavities and bubbles. Like, for example, in Cygnus X1, there's kind of still the debate about whether the wind from the companion star is helping to kind of blow up the cavity too. So that's a bit of another uncertainty that we have to deal with too. But on Greg's idea of trying to probe these interactions during outbursts, I think I agree with what's been said in terms of like, we don't really know the timescales of how these things are created. So I'm not sure we would see anything if we try and probe these things during outbursts, maybe like after an outburst to look for kind of a cavity or something like that. But I'm not sure that looking in outburst is really gonna give us any kind of detections. But, and then the last point that I wanted to just kind of make was an advantage of the technique that I've been using with the astrochemical tracers, the molecular lines, is kind of what I think Stefan already just said, is that we can get like a lot of different sort of morphologies for these kind of things, from like bubbles to hot spots to cavities. So the big advantage of using the molecular lines is we're able to kind of actually probe all these different kind of morphologies, where say if you're looking with like just the radio continuum, you know, the structure might not be bright enough. So it allows us to get at all these kind of different morphologies and hopefully allow us to find more of these. But we are trying to get in more telescope time, especially on ALMA, to kind of do more of these studies.
Thank you, Alex. I see another question online from Mukesh. Mukesh? Okay, well, we're trying to sort that out. Are there any other questions in the room?
Don't see.
Asaf, you have your hand up. Is that a historical hand, or is that a new question?
Oh, it's historical hand. That's
okay.
There's a question on Slack that just popped in. Do you see it?
1 sec. I think Mukesh is unmuted. Mukesh.
Yeah, I'm sorry. Yeah,
that's fine.
So I'm asking when a jet propagates with a relativistic speeds, and if it is turbulent, it loses energy through the turbulent dissipation, and it keeps on radiating its energy through radiation, of course, as well. So is it always correct to attribute this deceleration of jets to its interaction with the external medium, or it can be because of its internal dynamics as well?
I suppose it can also be due to its internal dynamics, which were kind of driven by its initial kinetic energy anyway, right? So I don't know if I can, I don't know if you can tell them apart.
I don't know how are we making with time, but well, just to come back to one of the points, do we need any other bands, for example? Is it just like radio to X-rays enough? Typically, they seems to agree, and it's just a simple power law. But okay, first of all, I don't know how long X-rays will be active, because Chandra is getting older, and first, it would be nice also to have a confirmation that there are no spectral breaks and which could be also interesting to understand how particle acceleration, or to have a confirmation that our models are correct in terms of particle acceleration and dissipation. So are there anyone that try to to go for infrared detection of this ejecta? Or, well, there was a VLT attempt, but then for 1820, I don't know if there was anybody that tried and did not succeed to get.
Many years ago, there was a paper by Sams, Eckhart, and Sunyaev. I mean, this was a long time ago, where they saw resolved infrared emission from GRS 1915 after a major radio outburst. And at the time, I don't recall, but I think they speculated, or there was speculation that this might have been dust, which had been impacted by the jet. It was in the early days of 1915, so maybe it was still interacting with its local environment. But I think it was also consistent with being synchrotron emission. But I mean, you know, as a general comment, I think in every case in X-ray binaries where we've seen the optically thin ejector at radio and at X-rays, it's been consistent with a single power law between radio and X-rays, probably without a radiative cooling break.
Yeah. I mean, Dave will probably, I think his hand's up. He's going to probably talk about the gravity and other ones. Yeah.
Dave, go ahead.
Hi, everyone. Yeah, so there was paper from, what was it, last year or the year before? Talked about this possibility of using the gravity instrument on the VLTI to detect on the milli-arcsecond scale ejector. It is very tricky, and we tried it so far just with Maxi 1820. But we really have to catch it at the right time over the transition, and gravity is not always available on the VLT. So I'm hopeful, because recent last few proposals have been accepted, but we haven't got any data yet. So there's that one possibility of being able to see it on the MAS scales. And then actually, I don't know if Christina Sbaglio is here, but she's leading a separate VLT proposal trying to get data with Force 2 on the VLT on the arcsecond to arc-minute scales for the longer time scale jets. We have done calculations based on the old XTJ 1550 detections in X-ray and radio that Rob and others mentioned, and given that source and two others, it is feasible if we catch it again at the right time. As long as the extinction is not too high, you can detect them in the optical, because they should be about 23 to 24, 25 magnitude. It's just about doable by the VLT. Last time the proposal was not accepted, and they said, "Oh, HST would have probably detected that if it was detectable." But I'm not convinced that people were looking for that with the HST. So I don't know if that's been done, but yeah, we're hoping to resubmit in a couple of days that proposal.
Dave, that's very interesting. Did you think about doing something which is more likely to be active when you observe it, like GRS 1915?
No, so, well, this second proposal on with using Force 2 in the optical is the TOO for the state transition of a typical transient. But we didn't think about 1915. It's a bit north for the VLT, but it is doable, I think. So
it's only plus 10, yeah.
Yeah, that's true. It'd have to be infrared, not optical.
Yes.
But yeah.
Yeah. Okay.
Yeah, that's worth thinking about.
Thanks. I see Poshak has his hand up as well.
So just related to that, I would definitely consider JWST now going forward. It's infrared. It's not interferometry, but you can probably get down to 0.01 pixels or so. So whatever that translates into in terms of spatial resolution, we'll have to work that out. And happy to take that offline, of course. I did have a question for you, Rob. Apologies if you mentioned this before, but have you ever seen multiple ejecta amongst these nice results that you're showing, like completely separate ejecta?
So if you look at this figure, Francesco will say more about this tomorrow, but if you look at this figure from Francesco's, you can see there's a second ejection event.
I see.
That occurs here. However, unless Francesco is going to reveal something that I don't know tomorrow, then I don't think we managed to track this one far out to see it decelerate.
Okay, and is the position angle the same, or is there any precession? Or
I think it was the same, but yeah, tomorrow morning. Morning.
Yeah. Francesco is here. Maybe can add one just.
Still Francesco, if I can answer to the
go ahead,
question.
please.
Yes, for example, in the case of a source I studied, Maxi 1348, we see a double ejection. So two components going in the same direction. The second one, 2 or 3 months after the first. And actually the second ejecta appeared to be as fast as the first one, but we didn't detect it at large scale as the first one. We didn't see any deceleration of the second component. And for which reason, I don't know, actually.
So we don't spoil too much your talk. Actually, we did the discussion a bit in anticipation of most of the talk. But
yes,
that's right. That's right.
But then, so Pierre Petrucci speaking, but then is it not surprising to not see any precession? I mean, for example, we have two blobs separated by a few months, if I understand correctly, and they have exactly the same direction, right? So,
I mean, Pop, there have been 20 sets of observations of GRS 1915 over the years, and the jets always go at the same angle. I mean, there are evidences of precession, but in most cases, I mean, the only X-ray binary jet with large-scale precession observed, as I remember, is SS433. Everything else, they go in the same direction or very close to it. Of course, on very small scales, V404 SIG seem to show a precessing jet, but on large scales, no. I think, did you want to follow up on that?
I was just going to comment on message 1820, or not 1820, shoot. Now I'm forgetting the source. I believe that Callum Wood's paper recently showed on VLBI scales also multiple ejecta for a black hole source, and now it's completely going in my mind. So just give me 1 second to search on.
It's 1820, Greg.
Okay, it is 1820.
This figure is from Callum Wood's paper.
Yes. So that one does it. Yeah. So we definitely see. So you see multiple ejecta in multiple jets from the same outburst.
Yeah, but I mean, I have to recommend everybody who's interested, who hasn't seen it, read Callum Wood's paper. It's extraordinary. There's a brief summary in this little box here of what happens, but we see Callum sees ejection of a component moving at about 0.3 C, significantly before the major event. Then there's a phase of type B QPOs as detected by Jeroen Homan. We see a radio flare which starts with Amy. We see a radio flare which peaks with Amy. And that radio flare appears to be connected to the superluminal ejections. And if you look in detail, you essentially, and really read the paper, you see that the superluminal, the relativistic ejections, they pass through, or at least pass by the earlier launched, slower moving ejector. It's extraordinary.
Okay, any other question in the room? Okay, there is Francesco that has 1 point.
Sorry, this is more a general question for you, for everyone. I just like to ask, since we still don't know the composition of this ejecta, which observations could be like preferred or could be useful for trying to understand the composition, if it's electron, positron, plasma, or if there are protons?
So from the side of AGN, I can tell you that we are not in a better position, because I think we are still debating since many years what is the composition of AGN jets, and having possibly more observations. For XRBs, for binaries, well, for AGN jets, one of the standard way was to compare what was the total power in the cavities with the power that we were getting from the jets from different kind of modelings. And this was suggesting that we have like jet. Okay, there is not a general consensus, but based on that, there was like electron proton, but the ratio, the right ratio is not clearly known. I don't know exactly what's the status for X-ray binaries. At some point, there was also some claim that baryonic jets were found based, I think, on the detection of absorption lines, but I'm not sure what happened then.
I could add a couple of comments. I mean, there is, of course, the case of SS433 where we see the atomic emission lines. However, I must admit, I suspect that what's happening in that case is that a highly relativistic inner jet is just pounding on the circumbinary material, and what we see is a secondary project. For the methods for determining, of course, you might look for electron positron annihilation, but the trouble is the timescales for the electrons and positrons to cool enough to annihilate it's a very long time. The other thing which there was a buzz about in the past, that was something that I was also briefly involved in, is the idea that circular polarization in an optically thin synchrotron plasma will tell you. So if you just naively, if you have electrons and protons, you'll get circular polarization. If you have electrons and positrons, you'll get no net circular, because the electrons and positrons spiral around the magnetic field lines in opposite senses. So for a while, it was thought that detection of circular polarization from jet plasmas might be a way of determining the nature of the material inside it. And this was relatively big in both AGN and X-ray binary jets. And we made detections in both classes of objects. The trouble is, it was quite soon realized that actually propagation of synchrotron emission within the plasma, because the plasma is birefringent, means that you can turn linear to circular. So it turned out that all the results were extremely ambiguous, and you couldn't really get anywhere.
Can I maybe add just one point? I mean, the hard part here is that, you know, you could start with a pretty leptonic jet, and then it's going to, because of instabilities along the edge as it's propagating, it's going to entrain matter. And by the time you get to the end of it, it could have a lot of hadronic material. And I think, you know, that complicates also the interpretation of the deceleration to some extent. And people are, you know, the problem is you could simulate, you know, jets at very large scales, but connecting it back to the core all the way out to those distances, you know, is still quite difficult. There's some simulations now that are showing entrainment. You know, Kaushik Chatterjee has done some simulations on that for AGN. But again, you know, if you want to connect it from the root of the problem all the way out to the scales you're looking at in a consistent simulation with that kind of resolution is hard. So I think we're still back to, you know, shrugging a little bit.
Yeah, I agree. Alex has her hand up.
Oh yeah, I just wanted to say, I'll briefly talk about this kind of composition issue in my talk later, but there's also some recent work that suggests looking in like the TeV gamma ray part of the spectrum might allow us to discern whether there are hadronic processes happening in the jet. So, and I'll talk a bit about that more in my talk later this morning.
Yeah, that's a good point. Thank you.
Yeah, Dimitris is mentioning this. I think he has a poster. The hard part is that he shows it's going to be very hard, even with CTA, to see the low mass X-ray binaries, potentially, maybe only the high mass.
Okay. Julia, were there any more questions in the room?
No, I think we're ready for lunch.
Okay. Sarah, I think we're pretty close to the end of our time, so I'll hand back to you.
It looks right. I mean, I had thought since we started earlier, we'd have time to open it up, but I think given the time, it's probably best to just give people the break and come back at 4, right? Do the LOC have anything they want to bring up at this point?
No. See you at 4.